Hello and welcome to another video tutorial of the EMDLAB software. In this video, we will be talking about the electric torque calculation, a complex topic actually, because we have various methods for calculation of the electric torque. We can use the energy co-energy method, the virtual work. We can use the Maxwell stress tensor method or other methods like the RQ method that is used actually similar to the Maxwell stress tensor by calculation of the average values on the air gap region. Anyway, so we will discuss the formulations, the details later in the future videos. And in this video, just I am going to explain how we can calculate the torque using the software, the methods, and the code that we need to use. So here in the ANSYS Maxwell software, when we perform the magnetic loading analysis, we can calculate the flux density waveform in air gap. Okay, the radial component of the flux density in air gap. Here, I consider this polyline in the middle of the air gap, and this is the BR. Also, we can calculate the tangential component and calculate the electric torque using the Maxwell stress tensor. So let's set the position of the rotor equal to minus 15. In this case, we have a positive electric torque. And here we have these parameters. I'm going to calculate the electric torque. So parameters, torque, positive. So when I run this magneto-static analysis, I can calculate the developed electric torque. As you know, we can sweep over the rotor position to calculate the static torque curve of the Swiss reluctance motor. So first, let's set the rotor position equal to 0. I want to calculate the flux waveform using the Maxwell and also the flux density waveform using the EMDLAB and Comparative. So if I run this simulation, here you can see the flux waveform. Okay, the peak value is close to 1.6. In EMDLAB, let's set the rotor position equal to 0, run the code. Okay, here we have the geometry, the mesh, and this is the flux density. Using this function, we can plot the BR and BT on circle. The center of the circle is 0 and 0. This is the radius of the circle, is the middle of the air gap, and the number of points that we are going to interpolate the value of the BR and BT. So if I run this method, here you can see the BR and BT. The peak value is close to 1.6. Okay, and this is the tangential flux density. So We can calculate the electric torque using this command s dot eval electric torque. Let's use the RQ method. What is the region that we are going to use the RQ method on? It is the air gap, and also we need to pass the thickness of the air gap. Okay, that is actually global variable gap. In this case, the value of the electric torque is 0. Yes, because the rotor is in its aligned position. We don't have the right electric torque here. So now if I set the rotor position equal to this one, minus 15, and run the simulation, we can calculate the electric torque using the ANSYS Maxwell and also using the EMDLAB. So here, the magneto-static report data table, torque 1, I should multiply it by the stack length of the motor. The value is 5.27. So let's increase the font size. In the switch reluctance motor design course, we discussed these topics. Okay, so you can refer to the related videos. Now let's calculate the torque using the EMDLAB. So set the rotor position, and here evaluate the torque by RQ method is equal to 5.36, 5.27, right? Is close. Also, we can use the Maxwell stress tensor, eval torque by Maxwell stress tensor. The inputs are actually, if I copy this and paste it here, you can watch the inputs, right? We need to set the center of the circumferential circle actually, and its radius, global variable, ISD divided by 2 minus gap divided by 2. That actually the circle that we are going to implement the Maxwell stress tensor. The value of the electric torque is 5.31. So, to calculate the electric torque correct, we need to use a fine mesh in air gap. And here, as you can see, we can handle the mesh density of the air gap using this number. We discussed this function before. And if I repeat the simulation, here in this case, we have a fine mesh in air gap, 2 layers of the mesh. Let's repeat the MST is 5.41. And here also we can increase the number of mesh layers when we defined the air gap. For example, if I use 4 layers and calculate the torque using the previous methods, MST is 5.2, and using the RQ method is 5.36, right? 5.2 and 5.27. So we need to use a fine mesh, especially when we are going to do the harmonic analysis of the air gap field. So let's plot the BR and BT on, right, this circle in air gap in this case when we consider this fine mesh. So how we can use the energy co-energy method? As you know, in this case, in this motor, we have a excitation on phase A, and also the mechanical position is the rotor position. So the co-energy, as you know, is a function of theta r and the current of the phase A. So the developed electric torque is the partial derivative of the co-energy with respect to the theta r. Derivative of the co-energy or negative of the derivative of the energy. So here in this design, I defined this optimetric analysis. Let me clean up the solutions. I defined this static torque analysis and also this parametric analysis here to change the rotor position from the completely unaligned position to the aligned position. And also I defined these two variables, the EC, this is the co-energy, and also I defined the energy here. In the right calculator, here you can define your calculations, field calculations. So I calculated the total energy and total co-energy. Let's increase the font size again. Here you can see the total energy and the total co-energy. For this rotor position, as you can see, the total energy is 0.63 and the total co-energy is 0.79. So here we can calculate the co-energy, energy and co-energy using this function s dot evaluate total energy co-energy. As you can see, the total energy is 0.64. Here is 0.63. Co-energy is 0.79. 0.79, right? That is close. Even you can plot s dot plot the energy during the solving of the problem. Iteration number of the solver, we have 6 iterations, right? And this is the value of the energy after convergence. Okay, so yes, we can change the rotor position, calculate the total co-energy and energy, and use this function. So in ANSYS Maxwell, here in this static characteristic, I defined the total co-energy in the field calculator, and let's run this parametric setup. So we can calculate the torque using the optimetrics that we defined and also using the co-energy method. So here you can see the static torque graph, this one, the red one, and here is the derivative of the co-energy. I multiplied it by the LS tank. Okay, so here you can compare. This is calculated by this equation, derivative of the co-energy, and this is calculated by the ANSYS Maxwell by defining this torque. This is derivative of the co-energy. So yes, we did this comparison in ANSYS Maxwell. Let me delete this one and export this graph, a static torque. Let's open it and plot in the Excel this graph. let's calculate the torque using the EMDLAB and compare. So here we can change this parameter, okay, and repeat the simulations and finally calculate the static torque. So let me copy and paste this code. Actually, we don't need to generate the mesh again and again, okay, but here in this video I use this method. In future videos I will use an improved method. Just we need to remesh the air gap. We don't need to remesh everything. So to keep things simple, just I'm going to use this case torque calculation. So here let's write this code. Actually we need to define a for loop here. This is the torque, an empty array. Change the rotor position from -30 to 0. Consider how many points we have here. 30 points. And also here I consider 30 points. I repeat everything. And finally, the torque and +1 is this one. Calculate the torque by the RQ method or the Maxwell stress tensor. Let me record both. So this is torque 1 and this is the torque 2. Also let me record the co-energy, right? Co-energy. We can calculate the electric torque by the co-energy. So here, this is the torque 1. The torque 2 is calculate the torque by the Maxwell stress tensor. And this is the co-energy is this one. S dot eval energy, total energy, co-energy. And just I want to plot the Bmag F, you know. I don't need to plot the mesh zones again and again. So here, let's highlight this line of the code. Show a sketch, the mesh zones, plot, where we have the show mesh zones. Here, just let's plot the Bmag F. So if I run this code, as you can see, we are changing the rotor position and running these magneto-static simulations. Even you can export images, right, to generate animations. So then we can export the torque 1 and torque 2 and compare. These the curves that we calculated using the ANSYS Maxwell. So here, the torque 1 is this one. So if I copy it, this is calculated by the RQ method. So yes, this graph, and yes, we have lots of figures, close all, torque 2. This is calculated by the Maxwell stress tensor, the MST. This one. Okay. So the RQ method works better, right? And finally, we can calculate the electric torque using the co-energy method. We have this co-energy, so we should use actually this equation. Derivative of the co-energy with respect to the theta r. So we have different methods. We can use the central difference, the co-energy with respect to the delta theta. In this case is pi divided by 6 divided by 29 is actually the delta theta. Okay, so the transpose of this expression is this one. This is calculated by the co-energy method. Okay, so the co-energy method, right, is close to this one, the RQ method. So we calculated the electric torque using 3 different methods and compared. Also, we compared with the calculated torque using the ANSYS Maxwell software. The Maxwell stress tensor method is sensitive, right? Is sensitive, and the RQ method and the co-energy method are better. Anyway, so you can repeat this code, this simulation, and let's continue investigating other methods in the next videos. Thanks for watching.